Okay, so in this video we'll talk about one other aspect of quantum circuits, which is their reversibility. And this is, it turns out to be something that's eventually simple to deal with, but it's something that we have to tackle. So quantum computers are always reversible. So what do we mean by that? So let's say you have a quantum circuit U. It takes as input the state x. So the output is u times x. Now I claim that there is some quantum circuit which undoes this, and on input u times x it'll output x. So what does this quantum circuit look like? It's just u dagger, right? U is unitary, and so we know that u times u dagger equal to u dagger times u is the identity. In fact, there's something even more that's true, which is that if you look at the gates inside of U, you can just take these gates, and in U dagger you just create the corresponding gates G dagger, G prime dagger, and so on, in the opposite order. And so what happens is when you put these two circuits together, then this gate annihilates that one, and the next gate here will then annihilate that one, and so on, because each one is a conjugate transpose of the corresponding one. And so these two circuits completely annihilate each other, and so what you have is the identity map, which just maps x to itself. Okay, so that's what we mean by saying that quantum computers are reversible, meaning that whatever you compute, you can also uncompute, if you like, by just doing the opposite of what you did to get there. Okay, so now let's see what this means if you're just trying to implement a classical circuit. So for example, a classical circuit might be doing something like, it might take as input n bits and output 1 bit, and it's computing some function f, a Boolean function f, on input x. So now, how would we actually compute this quantumly? Well, we'd have some quantum circuit for computing f, which on input x, so there are n wires coming in, and we want one of the wires on the output to contain f of x. And of course, you remember in a quantum circuit, if there are n inputs, there are always n outputs. And so from the reversibility property, it must be the case that we then should be able to compute, we should be able to uncompute this function and recover x from this output. But is it always possible to recover the input from the output? Well, think about an AND gate, right? So if you have an AND gate, it takes as input 2 bits A and B, and it outputs the bit A and B, which is 1 if and only if both the bits are 1, right? So this is equal to 1 if and only if A equal to B equal to 1 and 0 otherwise. So now, is there any way that this circuit could be, even if we output any other bit of our choice, is there any way of making this a reversible gate, a reversible circuit? And I claim it's not. So, just play with it and check that there's no way to recover A and B if you're given A and B as one of the outputs, and something arbitrary for the second bit. You could choose it to be B, you could choose it to be A or B. Just choose it to be anything you want, and check that there isn't enough information in this to tell you about what the two input bits are. You see, because why is that? Well, because if if the AND of these two bits is 0, then there are three possibilities that are consistent with it. But this bit, whatever this output bit is, no matter how you create it, it can only tell you about two possibilities. So there's no way we could identify which of the three pre-images we came from by only two different possibilities here. Okay, so clearly, if we were to go ahead and implement our function in a straightforward way, it would not be reversible. So what can we do? Okay, so what we want to do is somehow we want to feed in the input x as well as an answer bit b. So we think of b as initially being 0. So it's a place where the answer is going to be stored. And we want our quantum circuit to output x unchanged, but also the answer f of x. And maybe, what it does is it XORs b with f of x. So it takes the sum mod 2 of the two. So it flips b if and only if f of x equal to 1. And now, if you were to compute u sub f again, well, this would undo everything and it would restore the state of this output bit. Okay, so this is what we want to do ideally. And so let's try to see that we can actually implement our basic gates in a reversible manner. So let's start by looking at simple examples. What about the NOT gate? I claim it's already reversible, right? It takes as input the NOT gate we also called X, right? Because it takes as input a bit 0 or 1, and it outputs if the input was 0, then it outputs 1, and if the input is 1, it outputs 0. So that's already a reversible gate, and in fact the quantum analog of it is exactly the X gate which we know about. Similarly, if you were doing an XOR, it's like a C0 gate, takes as input 2 bits A and B, outputs A XOR B. And of course we know the C0 is its own inverse, so it's reversible. But what about the AND gate? That's the one we have trouble with. So now consider a control swap gate. So here's how we might write this control swap. Here's how we might draw it. So it has 3 wires. The first is a control, and then you have this second 2, where what this control wire does is, if the control wires are 1, then you swap the other 2. So you have A, and then B, C, and B and C get swapped if and only if A equal to 1. So why should this allow us to compute the AND of 2 bits? So imagine that we have C equal to 0. So now what's this output going to be? Well, if A is 0, then the output is 0. And if A is 1, then the output is B. So if A equal to 0, the output is 0. And if A equal to 1, the output is B. So this is another way of writing the AND function, because the only way the output is 1 is if A equal to 1 and B equal to 1. So this output is A and B. Okay, so this is a way of computing the AND gate in a way that's reversible, because the C swap gate is its own inverse. So now we have an AND gate, we have a NOT gate, so we have a NAND gate, and that's universal for classical computation. And so what we can do is given any classical circuit, we can replace all the NOT and the, well, we don't have to replace the NOT gates, but we can replace all the AND gates by swap gates. In the process, we may have to add in new fresh bits, which are initialized to zeros, and we get certain bits which are output which we didn't want, but that's okay because that's just junk bits. Okay, so this is how the construction then works. We are given some classical circuit. We want a reversible circuit which has exactly the same behavior, a classical reversible circuit. And so what we do is, well, assume that all the gates in here are NAND gates, and 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 NOT gates. The NOT gates are already reversible. AND gates we replace by these controlled swap gates. We feed in a number of fresh 0 bits to help the circuit run. And the output is going to be the output of the circuit plus some junk bits. Okay, so now is this good enough for our purposes? Well, how do we intend to use this in quantum computing? So imagine that we had this circuit, and what we wanted was a unitary transformation which would do the same thing for us. Okay, so what we really want is, once we have this reversible circuit, we can actually think about each of its constituent gates as being a unitary transformation. Okay, because if you go back to each of the constituent gates, it's a NOT, C NOT, and C swap, and all these are unitaries. And so this circuit can actually be implemented by a sequence of unitary gates. And so we can equivalently write down a unitary circuit corresponding to this, which on input X and zeros will output C of X and junk of X. Right? This junk is going to be a function of X in general. Okay, so why do we want to do this? Well, because now we can also ask what happens if we provide this input not as a classical state but as a superposition over all possible X. So we might feed in sum over X, alpha X, X, and this register could be all zeros. These remaining bits are all zeros. Now what's the output going to be? Well, remember a quantum circuit is linear, so the output is sum over X, alpha X, C of X, and then this register is going to be junk of X. Well, the junk of X we don't want, so can't we just throw this away and be done with it? Okay, so we are going to argue that in fact this junk is really critical, and we really don't want it there. And even if you throw it away, it's going to cause trouble for us. That's because of the rules of quantum mechanics. So let's see that in a moment. So what we'll see is that this is not the circuit that we want to end up with. The circuit that we want to end up with, the reversible circuit we want to end up with, is one that actually erases the junk and in its place leaves the input string X. So it takes as input X and a bunch of zeros. It outputs X as well as C of X, the output of the original circuit, and some zeros. So for us, this situation is infinitely preferable to that one. This is really not good for us. So let's see why that's the case, and let's see how to make this happen.